All right, let's get right into it. Today, we're tackling a really critical issue that's been bubbling up in power systems engineering. It turns out the very standards we trust for fault analysis, the rule books we all live by, might be giving us some seriously misleading, even dangerous results now that the grid is packed with inverter-based resources. So here's our game plan. We're going to start with the weird anomaly that kicked off this whole investigation. Then we'll look at the standards themselves, a tale of two different methods. We'll talk about the new grid and the rise of converters, and then pinpoint exactly where our models are completely breaking down. Of course, we'll look at the hard data, and we'll wrap up by looking at the next big challenge that's already knocking at the door. Okay, so every good engineering investigation starts with a puzzle, right? And for the folks working on this, it was a real head-scratcher. The question that kept coming up was simple but profound. Why are our trusted, industry-standard fault simulations suddenly spitting out numbers that just look, well, physically impossible? So engineers were running their routine short-circuit studies, just like they've done thousands of times. But something was way off. The results were predicting fault levels that seemed way too high. And even weirder, they were seeing voltage rises during a fault. Now, as you know, that just doesn't happen. It flies in the face of basic physics and was a huge red flag that something in the calculation was fundamentally broken. So naturally, this anomaly made everyone take a hard look at the rule books themselves, the international and national standards that we all use for these absolutely critical calculations. And let's just quickly remember why this is so important. A short-circuit study isn't some academic exercise, right? It's all about safety. It's about reliability. You have to know the absolute worst-case fault current that your equipment is going to see so you can specify a circuit breaker that will actually work instead of, catastrophically failing when you need it most. Now, the two main standards in play here are the international IEC 60909 and the UK's ENA G74. And the big difference comes down to how they figure out the pre-fault voltage. IEC 6909 uses these simplified, intentionally conservative C factors, basically just a voltage multiplier to be on the safe side. ENA G74, on the other hand, is a bit more sophisticated. It uses a full load flow calculation to get a more accurate pre-fault voltage, which almost always gives you a more realistic and usually lower fault level. But here's the catch. IEC 6909 is getting a bit long in the tooth. Its last big update was back in 2016, and the grid has changed a lot since then. And while the newer ENA G74 does try to account for what's called converter-fed generation, or CFG, it still doesn't quite nail the complex, dynamic way these new devices actually behave when a fault hits the system. And this gets us right to the heart of the problem. The environment, the grid itself, that these standards are trying to model has fundamentally changed from the ground up. The star of this new grid is converter-fed generation. We're talking solar farms, wind turbines, big battery storage systems. Unlike the old days of massive, spinning, synchronous generators, big chunks of rotating metal, all these new resources connect to the grid through incredibly complex power electronic inverters. And this is the absolute key takeaway. An inverter just does not respond to a fault the same way a big synchronous machine does. Its behavior isn't governed by physical inertia. It's dictated by software and control logic. All the old assumptions we've relied on for decades, they're pretty much out the window. Okay, so we've got old standards and a new grid. That brings us to the crime scene. Where exactly do these models completely fall apart? To understand this, we need to talk about a concept called retained voltage. So when a fault happens, the voltage right at that spot collapses to zero. But everywhere else on the network, the voltage just dips. That level it dips to is the retained voltage. And for an inverter's control system, that's the most important signal it's looking at. So here is the massive disconnect. The standards drastically, and I mean drastically, oversimplify things. They basically model a super sophisticated inverter as a dumb, constant current source that just blindly injects, say, 1.1 to 1.5 per unit current anytime there's a fault. The physical reality? The inverter's output is this complex, highly voltage-dependent response that's all managed by its fault ride-through control logic. And here is the killer detail, the one thing that breaks the whole model. That reactive current injection, the thing the inverter does to help support the grid during a fault, it doesn't just happen automatically. It only triggers if that retained voltage we just talked about drops below a very specific threshold. If the voltage dip isn't bad enough, the inverter's control logic just sits there and does nothing. So what happens when your model gets this wrong?
Well, the model assumes the inverter is always injecting current, even when it isn't. So it mathematically adds this phantom current injection across the network impedance, and the result is a calculated voltage rise at the bus. It's a ghost in the machine, a purely mathematical artifact that creates a result that is physically impossible.
Okay, so enough with the theory, let's look at the numbers from the study. This is where it all becomes crystal clear, and the problem is just undeniable. This table says it all. Just look at that IAC 6099 column. As you ramp up the amount of converter-fed generation on the system from 50 up to 200 MVA, the calculated retained voltage just keeps climbing to this ridiculous 1.53 per unit. Meanwhile, look at the ENA G74 column. It stays stable, right around 0.97, 0.98 per unit, exactly where you'd physically expect it to be. And this chart just drives the point home, doesn't it? In that 200 MVA case, the IEC standard is overestimating the retained voltage by over 50%. This isn't a small rounding error. It is a fundamental misrepresentation of what is actually happening on the grid. And this has huge real-world consequences. It's not just an academic argument. In one of the test networks, the real fault level was around 55 kiloamps. The flawed IEC model calculated it at over 71 kiloamps. An overestimation like that could easily lead an engineer to specify much more expensive switchgear than is actually needed, potentially costing a project millions of dollars. So to boil it all down, and this is a quote straight from the research, the entire problem is caused by the standards completely failing to consider that a grid-following inverter's fault response is conditional. It's not always on. It only kicks in if the retained voltage drops below that critical threshold. Simple as that. And just when you think, okay, we've got a handle on the problem with today's grid-following inverters, well, the technology's already taking another giant leap forward. Get ready for grid-forming inverters. These things are way more advanced. They can actually create their own voltage and frequency reference, behaving a lot more like a traditional generator. They're being deployed at scale right now, and here's the scary part. Our standards are completely unprepared. There is literally no agreed-upon method in any standard for how to model their fault contribution. Any approach used today is just a rough approximation. We're essentially flying blind. So this leaves us with a really urgent question. As our grid continues to transform at lightning speed, our most fundamental tools for ensuring its safety and stability are falling further and further behind. The question for all of us is, how do we update these essential standards before they go from being just a little inaccurate to being critically, dangerously obsolete?